Hi students. So after long back I'm uploading a YouTube video. So in this video we will discuss the slopes and deflection. So it comes under in strength of material subject. What is meant by slope and what is meant by deflection. So if you consider a beam, this is simply supported beam and it carrying a either uniformly distributed load or any point load. Okay, so the beam is changes its original shape. So this changes we may call it as a deflection. See here, so this is a deflection diagram and this is the deflection we are going to denote by the Y. Okay, so if the beam is carrying uniformly distributed load or whatever load it is, so the beam is changes its original shape. So this one we may call it as a deflection, and deflection is denoted by the Y. And let us move to the what is meant by slope. Slope means if you are going to draw a tangent this deflection diagram, if you are going to draw a tangent to this deflection diagram at any point. So for example, I'll draw the tangent like this, whatever it is. If you are going to draw a tangent to this deflection curve, and what is that angle from original to this tangent line, so this one we may call it as a slope. So again I'm repeating. So draw the tangent to the deflection diagram, and what is the angle between a beam to this tangent line, or what is the angle between this original beam to this tangent line, we may call it as a slope. So this is the basic definition of slopes and deflection, and how it occurs and how to calculate like this. So before going to in detail, so I'll go with small definitions. So y, if you are going to differentiate this y, will be equals to the dy by dx, and again you will differentiate. Finally we got d square y by dx square, and again you will differentiate, you will get the d square y, d cube y by dx cube. So what is this y? Why I am taking why I am saying all these parameters means, so there is an interlink between all those things. So y stands for here deflection. So y stands for deflection. If you are going to differentiate this deflection means y, you will get the slope. So it means dy by dx may call it as a slope, and again you will differentiate, you will get the moment, and again you will differentiate, finally you got shear force. So there is a interlink between each and every category. So you are going to differentiate y, and finally it reaches to the d cube y by dx cube. Okay, these are all very important terms in the civil engineering point of view, and these are very useful for in future also. Okay, fine. So we already finished what is meant by slope and what is meant by deflection, and now how to solve or how to get the slopes and deflections. Is there any methods? Yes, we are having 4 methods to calculate the slopes and deflections. We are having 4 methods. So what are those? We will discuss now. So first one is Macaulay's method. Second one is moment area method. Third one is double integration method. double integration method. And last one is, fourth one is conjugate beam method. Conjugate beam method. So these are all four types of methods to calculate slopes and deflection. Okay, so in this video I am discussing only moment area method. Okay, in this video I am going to discussing only moment area method. So by using this moment area method, how to solve the slopes and deflection with the different beams and different loading conditions. So let us move to the moment area method. So moment area method is also known as Moore's theorems. Moore's theorems. So other name you can call it as a Moore's theorem. So in this Moore's theorems, we are having two types of statements: Moore's theorem 1 and Moore's theorem 2. Okay, so Moore's theorems having two categories: Moore's theorem 1 and Moore's theorem 2. So what stands for 1 and what stands for 2 we'll discuss. So 1 stands for, Moore's theorem 1 stands for, it defines the slope, that is dy by dx, or slope is denotes by not only dy by dx, it also defines theta also. So Moore's theorem 1 defines the slope. So what is that? So area of the bending moment diagram, area of, so everyone listen, area of the bending moment diagram of a beam divided by the flexural rigidity. So I am repeating one more time. So area of the, so bending moment diagram, area of the bending moment diagram divided by the flexural rigidity gives the slope at particular point. Okay, area of the bending moment diagram divided by the flexural rigidity gives the slope at the particular point. And next one, this is the first theorem. Okay, now second theorem states that, it states deflection. Okay, so deflection is denotes by the y. Okay, what is this statement means? Moment of, so listen carefully, moment of area of bending moment diagram, moment of area of bending moment diagram, so divided by flexural rigidity gives the slope at, deflection at particular point. Okay, so Moore's theorem 2 statement is moment of area of bending moment diagram divided by the flexural rigidity gives the deflection at the particular point. So Moore's theorem, simply we can say it as area by EI, and deflection, that is Moore's theorem statement 2 states that A into x bar divided by EI. So these two are Moore's theorem statement. So another called as moment area method. Here the A stands for area of bending moment diagram, and x bar stands for, here x bar stands for centroidal distance. So based upon these two cases, based upon these two formulas, we are going to discuss with the different beams, cantilever beam, simply supported beam with loading conditions. So let us move to the, first of all, cantilever beam. So how to solve the cantilever beam slopes and deflection. So first case, so cantilever beam carrying a point load at the free end, cantilever beam carrying point load at the free end, and the span is L meters, and the span is L meter. And what is the slope and what is the deflection? So where the slope and deflection occurs means at the free end only. Why? Because this is the load is acting at the free end, so that you will expect slope and deflection at the free end. Okay, so we know that statement 1 is equals to area by EI, and statement 2 is equals to area into x bar by E. X bar is centroidal distance. Okay, now what is this area? Bending moment area. You just remember bending moment area. Okay, so first of all, what is the bending moment diagram for this case? So if you consider this is A point, and if you consider this is a B point, now I am going to calculate moment about A. So what will come? So load into perpendicular distance. What is the load here? W into perpendicular distance, W into L. Now you just forgot about the plus and minus. Okay, you just note down what is the moment. What is the moment will come? Force into perpendicular distance. Okay, now so what is the diagram? See, this is the bending moment diagram. At B value is 0 and at A value is, we will get W into L. This is the bending moment diagram, and you will get it is just like a triangular. Okay, and this value is W into W into L. This value is WL. Okay, and I need to calculate the slope at this particular point and the deflection at this particular point. So what is the statement? Area by the EI. So therefore theta B is equals to, what is the area? Area of the triangle means half into base into ordinate. So what is the base is here? Length be the base, and what is the ordinate here? W into L. So that half into base is L, half into base is L, and what is the ordinate? W into L, and it is divided by EI. Finally you got W into L into L means L square, and it is divided by 2i. Finally this 2 and EI be the product. So finally theta at B is equals to WL square by 2EI. See this, very simple, very simple concept to define slope and deflection of cantilever beam carrying a point load at the free end. And this is the slope value. And now what is the deflection at this point B? See, we will see the deflection. Same thing, it doesn't change the area, but extra thing here, x bar. What is the x bar here? So what is the x bar? So from this, it is a, what is the centroid of a triangle? 2/3 of the distance. Here it is a base means, so that you have to consider 2/3 of L. So therefore y is equal to deflection at B is equals to, so YP is equals to same, area doesn't change, that is half into L into W into L into, what is the x bar here? 2/3 of L. Here 2 to get and divided by EI, so divided by EI, 2 to get cancel. Finally we got W into L into L into L. Finally we got WL cube, and here 3 is there, divided by EI. See, therefore WL cube divided by 3EI. So everyone note down, cantilever beam carrying a point load at the free end What is the slope and deflection? Slope is WL square by 2EI and deflection is WL cube by 3EI. See, very simple to get the slope and deflection while in moment area method. Okay, so now we will go to the if cantilever beam carrying a uniformly distributed load. So what is the slope and deflection? We'll discuss now. So this is a cantilever beam and this is a uniformly distributed load. Now I am considering this intensity is W per meter. So formula doesn't change, and I am taking this is A, I am taking this is B. First of all, you have to calculate the moments. MB is equals to 0. So you already discussed in this shear force bending moment diagram chapter. MB is equal to 0, and finally MA is equals to, you will get W, that is load into, and the distance is here L. So load into L be the force, here the W per meter. So for every meter it is acting W. So for L meter it is a W into L, and where it is acting L by 2. So this is the moment about A. So W L square by 2. Okay, now you can draw the diagram. You can draw the diagram. See, so this is the diagram, and it is just like a parabola. Okay, it is just like a parabola, and this ordinate is W L square by 2. Concept is same. That is Mohs theorem 1 is applicable for slope and Mohs theorem is applicable for deflection. So now first theorem defines the slope, that is theta at B. I need to calculate what is the area of this parabola. So before going to explain this areas of parabolas, so we are having two types of parabolas. See, I'll explain. So you just consider this is a case. Yeah, this is first parabola, first type of parabola, and this is second type of parabola. Okay, this is first type of parabola and this is second type of parabola. Okay, and so this is the for this case centroid is 1/3 of base into height, and for this 2/3 of base into height, or AB means you may call it as B into H, whatever it is, but I am considering A into B. So 1/3 of base into height, and for this 2/3 of base into height, and centroids for this case very important. See, and for this 3/4 of whatever it is, either L or whatever it is, and this is 1/4. This is 3/4 and this is 1/4. If you consider this is a centroid, from here it is a 3/4. And now same thing, centroid for this type of parabola is, this is 5/8 of either it is distance or whatever it is, 5/8, and this is 3/8. See, again I am repeating. So here we have to consider two types of parabolas. Okay, so simply it is concave and convex, you can call it as. Okay, or otherwise hogging type of parabola and sagging type of parabola, whatever you required. So for this case 1/3 of base into height, for this case 2/3 of base into height, and the centroids are, so this is 3/4 and this is 1/4. Okay, and this is 5/8 times and this is 3/8 times. So I'll go with one clear sketch, and this is reverse sketch, you should not worry about. See, I am writing this is 3/4 and this is 1/4 and this is 3/8 and it is 5/8. Reverse sketch I am drawed. Why? Because so actually you will get the diagram like this. Okay, actually you will get the diagram for simply supported whatever is, this is the diagram. So that's why I noted like this. Okay, see, we will see the theta at B. So and the diagram is parabola, this is the parabola. So theta at B is equals to 1 by third of, so what is base here? L be the base, and what is the ordinate? W, L square by 2. See, this is the ordinate and this is the base, divided by EI. So finally got, that is equals to W L cube. See, L square into L stands for L cube, divided by 3 2s are 6 EI. W L cube by 6 EI. Okay, so this is the slope at point B. So now for deflection calculation, see, so that is y at B is equal to same concept, but extra is x bar, that is A into x bar by A. Just now I said to you, so what is the centroid for this? 3 by 4th of, from this we have to consider now, so that is a 3 by 4th of E. So area is same, so that is equals to 1 by third into L into W L square by 2. What is centroid here? 3 by 4th into L. Am I right? See, so this is 3 by 4th of here is there, and this is the 3 by 4th you have to consider, divided by EI, divided by EI. Finally 3 get cancelled, so W into L square into L, finally we got WL power 4 divided by 2 4 means here 8 and 8 EI. This is the final formula for deflection for cantilever beam carrying a uniformly distributed load. This is the formula. Okay, so for slope is WL cube by 6A. Now we will finish this cantilever case. So next one is, so we will discuss the simply supported case. So this is a simply supported beam now, and this is a central point load. If simply supported beam carrying a central point load L by 2, and this is L by 2. Okay, and what is the slope and what is the deflection? So concept is same. So first of all you have to calculate the reactions. So for this what is the reactions for this case? RA is equals to RB is equals to total load divided by 2. Am I right? Why? Because it is a symmetrical loading, so total load is W divided by 2. And for example, this is A, this is B, and this is C. What is the moment at this C? So moment at C is equals to reaction into L by 2. Reaction is here W by 2 into L by 2. Finally we got WL by 4. So and MA is becomes 0, MB becomes 0. You already know in shear force and bending moment diagram concept. So now I'm going to draw this diagram. See everyone. So this is the maximum bending moment occurs at this center, and the diagram is triangular. Am I right? And this value is WL by 4, and this value is WL by 4, and here it is moment is 0. So concept is that is, I mean, moments Morse theorem means first theorem statement is slope, and second theorem is statement is deflection. Now I'm either theta A or theta B, both are equal, so that theta A I'm calculating, so that is area, bending moment area divided by the flexural rigidity. What is area for this case? Only I am taking this half portion. I am considering only half of this portion. So what is the value for this case? area means here half into, now you can complicate it here, it is L by 2. You should not confuse about only half of the distance we are considering. So area means half into, what is the base here, L by 2. What is the ordinate, WL by 4. Ordinate is WL divided by 4 and divided by, what is the flux velocity, EI. So now you can calculate the case, that is equals to W into L into L square, 2 2s are 4, 4 4s are 16. So W L square by 16 EI. So what is the slope for simply supported beam? It is a W L square by 16 EI. Sorry, I didn't told one thing. For simply supported beam, maximum slope occurs at the supports only. Slope occurs maximum at supports only, and maximum deflection occurs at the where the load is acting. But for this case is at the center. Maximum deflection occurs at the center. So what is the value of slope? WL square by 16 EI, and it is same for theta B also. Okay, so now, and what is the deflection? Deflection y maximum, it is equals to, area is same, that is half into L by 2 into W L by 4, W L by 4, and you have to consider this is the centroid. So everyone here will confuse. You have to consider from A point, that is the centroid. You should not take from this case. Centroid is, that is 2/3 of length and divided by EI. 2/3 of length, sorry, not length, L by 2 means it is a distance is L by 2. So that's why you have to take L by 2. Okay, so finally got so 2 to get cancelled, and finally that is WL L cube. So WL cube, and final 2 4 ja 8, 8 3 ja 24, 24 2 ja 48. WL cube by 48 EI. Okay, you just for simply supported beam you have to consider from the ends only. Centroid you have to consider from the ends, you should not consider from the center. So just keep it in mind. So simply supported beam, maximum slope occurs at the supports and maximum deflection occurs where the load is acting, but in this case, so maximum deflection occurs at this center. So that's why maximum deflection at the center is WL cube by 48 EI. And the last derivation is simply supported beam, if the carrying is uniformly distributed load. See, simply supported beam carrying uniformly distributed load, and the intensity is W per meter and the span is L. I think all of you know about this bending moment diagram. Yeah, what is the bending moment diagram here? It is a parabola. Bending moment diagram is parabola, and this ordinate value is, everyone know, WL square by 8. So you need to if you want to calculate, you just go through this. First of all, RA is equals to, or first of all you have to calculate the reactions. RA is equals to RB is equals to total load divided by 2. Why? Because it is a symmetrical loading, WL by 2, and where the maximum bending moment occurs means at center, at the middle. I am considering C point, that is equals to RA into L by 2, RA into L by 2, and now minus load into L by 2 into L by 4 you will get. So finally you will get WL square by 2. If you calculate this one, WL square by 8. If you want to know how to get this WL square by 8 means this is the procedure. Okay, So concept is same. I'm repeating. Morse theorem 1 statement is for slope, Morse theorem statement 2 is for deflection. So first theorem statement is equal to, it defines the slope. So both the slopes are equal, theta a and theta b are equal. So I'm notating a notation I'm giving as a theta area by ei. So you have to consider area half of this portion. Okay, in the same in the previous problem also we are considering only half portion. Okay, so that is theta a or theta b, or both are equal. So what is the area of the parabola? Now it is very important criteria. So I already discussed in the cantilever case. See, so this is the diagram. So it is just like a, what is this? It is a sagging moment. So sagging parabola. So what is the area? 2/3 of base into height, and what centroids is 5/8, and this is a, so 3/8. So same thing we are going to discuss now. Okay, and the area is equals to 2/3 of, what is base here? Everyone will confuse, only you have to consider half portion, L/2 base into, what is the ordinate here? W, L square by 8, and divided by EI. So this is the statement. So 2 get cancelled. Finally we got W into L cube, 3 8 ja 24. So W L cube by 24 EI. W L cube by 24 EI. So see this very simple concept. So area of this parabola and divided by the flexural rigidity. Now Morse theorem statement 2 is along area with centroid you have to product. See, so Morse theorem statement 2 is y defines, that is equals to, same area is W 2/3 of L/2 into W L square by 8. This is the area. And what is the centroid? You have to consider from the supports. So for simply supported case only, 5/8 times of length, but length is here L/2, so that's why you have to consider 5/8 times of L. So 5 divided by 8 into span is L/2, only half of the portion we are considering. Why? Because the load is acting from this A point, it is not acting from the B point, the load is acting A point, so that's why you have to consider the centroid is from the supports. Okay, and divided by EI, and it is divided by EI. What is the value? Finally, if you solve this case, so 2 get cancelled. So W into L square, and here one more L is there, and here one more L is there. So 5 W L power 4 divided by 3 8 square is 64, 64 3 is, finally you got 384 by EI. 5 by 384 W L power 4 by EI. These are the this is the simply supported beam carrying UDL, and this is the slope, and this is the deflection value. See, very easy while considering moment area method or Morse theorem statement. But when coming to the another three methods are there. One is conjugate beam method and double integration method. Macaulay's method is also there. While compared to all these methods, moment area method is very easy to solve the slopes and deflections. Not only derivation, problems also very easy. And in the next video we will discuss the how to solve slopes and deflection by using conjugate beam method, and it is also very easy when compared to remaining Macaulay's method and double integration method. So now I am closing this session. So next video we'll discuss that deflection calculation in conjugate beam method. Thank you.